The OSI data link layer. This is the layer at which computers communicate directly over the physical media. Essentially, it's where the rubber meets the road. In this nugget, we're going to define a MAC address. Then we're going to find out how the MAC address discovery works. We're going to outline the processes involved in CSMA-CD, and we'll end up with a discussion on duplex modes. In defining a MAC address, I'm going to start by showing you what MAC stands for. We find it here. It stands for Media Access Control. Now, this name actually came from the fact that the data link layer has two sublayers. One is called LLC, which is Logical Link Control, and it addresses all matters above this layer. And then the bottom sublayer is the Media Access Control, and as it says, it's getting ready to access the media, and it's the control features to do that correctly. As with most popular identifiers, the MAC address does have aliases. You'll also hear it referred to as the Ethernet address, the physical address, and sometimes a burnt-in address. Alright, let's look at the makeup of how a MAC address is represented. First of all, it's a 48-bit address represented in hexadecimal. 48-bit or 6 bytes, and that's what you'll see here is 6 sections, 1, 2, 3, 4, 5, 6. Each 2-digit hex number is separated by colons. And you see that here as the colons divide each of the 6 bytes. So where do we find a MAC address is a really good question to ask at this point. And I'm going to show you on a Windows machine where that can be found, and it's going to be different depending on your operating system. But IP config -all will bring up quite a bit of information. What we're really concerned with right here is the physical address. Remember that I told you that the MAC address has many aliases, and the common one used within a Microsoft environment is the physical address, and I see here 00065B0159B7, which, by the way, is exactly what I have here. To avoid confusion and maybe even intimidation, let's take a detailed look at the hexadecimal numbering system and how it works to make you feel more comfortable with the representation of a MAC address in hex. Alright, the hexadecimal numbering system. It's a base 16 numbering system. What does that mean to us? Let's take a look at other numbering systems and their bases to give you an idea of what we're driving at. First of all, the decimal numbering system has a base of 10. The binary numbering system has a base of 2. We'll see that evident in their place values. Let's look down here. The decimal system has place values. In the first place value, there is a 1. In fact, all numbering systems are going to start with a 1 place value. At that point, you take the current value and multiply that by the base, which is 10, to come up with the next place value. So 1 times 10 is 10. Take this place value, multiply it by the base, 10 times 10, we come up with 100 for the next place. 100 times 10 is 1,000. And this would go on infinitely. But you understand that we increment multiplied by the base of the current number in each place. Let's look at the binary system. Again, we start with a 1. We multiply that current value by the base, we get a 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. 32 times 2 is 64. 64 times 2 is 128. At this point we stop. Most representations within the computing field are represented in octets, and we have 8 values here in our binary number system that represent an octet. So we stop here. Let's go on to the hex. Again, we start with a 1 place value. Multiply that current value by the base, which is 16, to get the next place value. Luckily with hex, we stop here. There's only 2 place values that we deal with, and the reason for that is, again, most numbers are represented in octets in computing. So a decimal value of 255 if every one of these place values was turned on. Well, if we turn each of these 2 values to their maximum range, we get a decimal equivalent of 255, so we don't need to go any further. Don't be concerned that the 255 didn't show up on your whiteboard. I'm simply ghostwriting to draw the point home, but at the same time keeping from cluttering the whiteboard. Alright, we spoke of ranges in each of these places. Let's talk about the ranges. In the decimal numbering system, we have a range of 0 to 9. What does that mean? That means in each of these place values, I can have a representation of a number from 0 to 9. If this was a 5, it'd be 5 times 1 equals 5. That's the value. But let's make it a little bit more complicated. If I had a 5 in the first place value and a 5 in the second, essentially what you would be working out is 5 times 1 is 5. 5 times 10 is 50. 50 plus 5 is 55. So you see how that works. Within the binary numbering system, The range is pretty easy. It's a 0 or a 1. And again, a 1 is representative of turning the value on, and a 0 is turning it off. So you have a 0 or 1 here, 0 or 1 here, 0 or 1 here, and that continues down the line. Now for a hex numbering system. Binary was really easy, and then we had to move into hex. This is a bit more complicated. We have values 0 through 9, as we did in decimal, available to us, but we also have the letter values A through F available to us. Why did this happen? Okay. We didn't want to take each place value and have a double-digit range underneath it. It would just get confusing if I had a 10 here and a 10 here, understanding how these lined up. So instead of doing that, if I wanted to represent tens, what I would do is I would use an A in that field. So now, A representing a 10 times 1, that's a 10 value in the ones field. And if I had a B in the 16th field, it'd be 11 times 16, which is 176 as a value. Remember earlier, I said we only need 2 placeholders within the hex numbering system because at their maximum range they would represent 255. Let's illustrate that. I have a 1s place and I have a 16 place. On the 1s, if I make that an F, again that's the top of our range representing 15, and in the 16s field represent an F as well, what I'm going to come up with is a 15 value in the 1s field, and in this field, 15 times 16 being 240. I add these two values up, and I come up with the decimal number 255, which again is the max of our range. Going back to our MAC address, let's look at the different parts. Here we have a standard MAC address. Again, it's what I pulled from the machine, and it's known as a universal MAC address, a UMA. There are 2 parts to every universal MAC address. The first part is a vendor ID. In this case, 0006 5 Bravo. This vendor ID is also known as an organizationally unique identifier, an OUI. This portion of the MAC address was named very well because it offers a unique identifier per organization. Essentially, the IEEE, which is a standards organization in the networking world, will hand out this 3-byte identifier to a specific company, and only that company can use this OUI for its universal MAC addresses. At this point, let's go to a very cool website. It's an IEEE website, and it enables us to look up OUIs. Alright, so in the search string here, I'm going to type in Dell Computer Corp, and let's see what we come up with. Alright, the first entry, 00065B, which by the way, is the OUI we're dealing with that I pulled off of this machine. So that tells you that this network interface card was produced by Dell. Let's do another one. This time, a little bit different though. Instead of typing in a company name here, I'm going to type in an OUI, 0000 Charlie, and let's see what we return. Exactly what we thought. You hear this in most classes and in most literature as being the OUI for Cisco, 00000 Charlie, and indeed it is. Cisco Systems right here. But take some caution, because if we come back and we type in Cisco at this point, look, we have many OUIs to choose from. So if you're sniffing a network and you see a network interface of a Cisco router and you expect 00000 Charlie, but you actually get 000142, don't be alarmed. There's nothing wrong with your sniffer, and there's no duplicate addresses on the network or anything like that. There is a myriad of OUIs that are available to Cisco systems. But remember, if you do see something strange, you can come to this website, type in Cisco, and find and correlate that OUI to the company. Alright, let's go back to our whiteboard. We discussed the first part of a MAC address. Now let's discuss the second. The second 3 bytes are vendor assigned. What does that mean? Alright, as I have a company that is assigned an OUI, like Dell Computing was here, then after that, the next 3 bytes, they can assign any number combination here as long as it is unique for every network interface card. What does this allow them? Approximately 16 million combinations. So they can make 16 million different UMAs out of one vendor ID. Isn't that awesome? Something else to note here though. All computers, like N1 and N2, communicate via MAC address. This was mentioned in the network layer nugget. Even though they have IP addresses, so they can route a message from one part of a network over to another, especially over routers, Once you're either on a local area network or even a wide area network, the key here is that I have two computers talking directly to each other. The communication is accomplished via MAC address. So now you can understand the importance of understanding the MAC address. Let me throw a little twist at you though. I'm going to add another host to this network, N3. And N3 is going to have its own universal MAC address as well. Now, if N1 wants to communicate a message to N2 and N3 simultaneously, can it do that? Because so far all I have is these unique identifiers that they can talk to each other by. So it would mean that N1 would have to talk to N2, pass the information, close that connection, and then talk to N3, pass the information, and close the connection. Fortunately, this isn't true. Let's look at why. There are different types of MAC addresses. The first is a unicast, and what we've covered so far. Its definition being a unique MAC address to one node. The next type we have is a multicast. This is a group of, but not all, nodes on the subnet. So in other words, on our last diagram, actually I'm going to add one more node to our diagram that we're going to work with down here. If N1 wants to communicate to N2 and N3, but not N4, one specific message, what they will do is become a part of the same multicast group. It's a specific identifier at the MAC address level that will send out one packet to both of these entities at the same time. Now the specifics on the numbering and the hex values within that MAC address are beyond the scope of the CCNA, but it's very interesting reading if you want to go forward with that. Alright, and the third type is a broadcast. This simply is a message going out to all nodes on the subnet. So if N1 sends out a broadcast, and the broadcast hex value at the MAC address is all F's in each of the 6 bytes, it will get out to N2, N3, and N4 with one transmission. You can imagine then the bandwidth savings that multicast and broadcast offer over simply having a unicast option only. So far, we've defined the MAC address. Now we're going to move into MAC discovery using a tool known as ARP. ARP stands for Address Resolution Protocol. I just love how intuitive the names are so far. You know, it's not true in all of networking. A lot of these acronyms don't give you a good hint as to what the protocol is doing, but in the case of ARP, it's resolving address problems. So let's take a look first at the datagram. We're going to have a data link header because we're talking about a piece of information that's at the data link layer. We're going to have some miscellaneous fields here that make up the IP header. And we're going to have a sender MAC address field, a sender IP field, a target MAC field, a target IP field, and a trailer. Alright, so let's look at a scenario. I have N1. It wants to talk to 192.168.1.253. It knows the IP address it wants to talk to, but again, these computers, being directly connected, have to talk via MAC address. It doesn't know the MAC address. So what does it do? It sends out an ARP request. And this is what the packet's going to look like. It's going to have the sender MAC, which is this value here in this field. So that we have. It's going to have the sender IP, 192.168.1.254, in this field. The target MAC. This is exactly the question. It's going to leave this blank and say, please fill this in. The target IP, 192.168.1.253, will be filled in here. Here's the trick though. We talked about the fact that all these devices talk via MAC address. I don't know the MAC address of N2, so how am I going to get this question to him in the first place to find out how I talk to him? The secret in that is what we covered just a minute ago, and that's the broadcast address. So a series of all F's is going to be set here for 6 bytes, as we said before, for a broadcast address in the data link header. What does that mean? That means that everybody on this wire is going to receive that packet. N3 is going to get it as well as N2. And they're both going to process it. N3 is going to look at it. As it gets up into the packet, it's going to understand that there's a question for a MAC address related to an IP address of 192.168.1.253. It looks at its address. I'm 192.168.1.252. It's not me, and it simply discards that packet. Doesn't answer, doesn't do anything with it. N2 is going to process it as well. Do the same thing. It's going to look at the target IP, match it against its own, and it's going to say, hey, that's me. I better reply. Now, in the reply, instead of having this broadcast traffic going across, when I received that request, I received the MAC address right here of the original sender. So now that's going to be in the data link header for the destination, and it goes on, but it's simply this MAC address. So now I'm having unicast type of traffic from N2 to N1. In the sender's MAC address, this is where we're going to put the answer to our question, because N2 is now the sender, where it was the target before. So it puts its MAC address here, puts its IP address here. The target MAC and target IP are those of N1, and you note that every field is filled now, and it sends this ARP reply to N1. Now that the MAC discovery is complete, I'm able to take step 3 here and deliver the original datagram that I wanted to send to N2. Now to keep this from happening every time I want to send information to N2, there is a cache within all computers, and you can set this administratively to whatever length of time you want, but for a period of time it's going to cache that 192.168.1.253 has a MAC address of the exact answer it got here, and it'll keep that in cache for a period of time. Address Resolution Protocol, a pretty streamlined process used to discover unknown MAC addresses. Now we're going to outline the processes involved in CSMA-CD. Again, we're going to start with breaking out the acronym. CS is carrier sense, MA is multiple access, CD is collision detection. To help you better understand CSMA-CD, let's start by looking at a common occurrence. What I have here is a four-way stop at an intersection. These represent cars. I know they probably don't look like cars, but that's what they're going to be for our analogy. These are stop signs. Alright, when I have a car here that gets to an intersection, the first thing I do is carrier sense. I look around at all points of the intersection to make sure that nobody else is going through. That can include cars, it may be pedestrians, it may be bikers, animals, anything. Why do I do that? Because there is multiple access. I don't own this intersection. There are other people, other vehicles that can go across here. Now, as I proceed into this intersection, I constantly watch still for other vehicles, cars, pedestrians, animals, for collision detection. And once a collision occurs, I'm going to have to go through a certain process to notify everybody of the collision and take care of the people that are involved. The same type of scenario plays out in the networking world. I have computers N1, N2, N3, and N4, all of which have a transmit pair and a receive pair on their physical media, and they're going to attach to what's commonly known as a common bus. In this architecture, I have one piece of shared cable or media that these signals are going to traverse. Now you'll see it a lot of times represented in a hub, which is a multi-port repeater. Alright, so let's say that N1 wants to send traffic across to N4. It's going to do just as this vehicle did. First thing it does, carrier sense. Is there anybody on this bus? If there's not, then I'm going to send my packet across the bus, watching and listening the whole time for a collision. If a collision occurs, now I have a protocol that I need to follow to let everybody know first that there has been a collision and to take care of retransmissions. How do I do that? I have a 32-bit jam signal that I send out of N1. As soon as I hear a collision, you know what, let's represent the collision. N1 sends out a packet. At the same exact time, N3 sends out a packet. At some point, they're going to meet. When that happens, you can measure the differences in the electrical signals on this cable, and N1 says, hey, that's a collision. 32-bit jam signal sent out across the wire. N3 sends the same signal to everybody, so everybody receives it. It says, hey, there's been a collision, there's been a collision. Now, every one of these computers is going to run a back-off algorithm. What this does is, it's a random set of time that each computer is going to wait before retransmission. It doesn't sound like it could be too successful, but it really is. It's very successful in the fact that once a collision has occurred, everybody backs off this random amount of time, and then they try to retransmit again. So N1 waits a random amount of time, retransmits. It will be different than N3, and the packet should get across. But let's say for the sake of argument that it's not. Let's say it is, or maybe it is. It's different than N3, but now N4 throws something out on the wire, and we keep getting collisions. This back-off algorithm will happen in a single computer 15 times, which is going to give you a total of 16 tried transmissions. If at that time you got 16 collisions, what it's going to do is the data link layer is no longer going to deal with this, and it's going to send it up to the higher layers to take care for retransmission. Let's say it was a TCP packet, then the TCP packet will time out and say, I haven't been acknowledged sending that packet, so let me try it again. So there you have the process of CSMA-CD. Now you could argue that if carrier sense was improved to the point that you didn't transmit on the wire until you were sure that there was nobody else transmitting, then we wouldn't need collision detection. And think of the time we would save and the bandwidth and the retransmission time. The problem is, it will never work on a shared bus. This is the part that hinders us and the reason we have to have collision detection. This same shared bus architecture is the reason for another rule that's imposed on computing. And it says that as N1, a computer, if I am transmitting on the wire, I shut down my receive pair. I cannot receive at the same time to save confusion on this common bus. This mode of communication is known as half duplex. Now there's two duplex modes that we're going to talk about. The first is half duplex. So I have the same architecture here that was on the previous whiteboard. N1 can transmit but cannot receive because of the shared bus that it rides on here. So, at some point though, somebody had to connect two PCs back to back, N1 and N2. And they said, I have a transmit pair. I'm transmitting from N1 to N2. By rule, I am not allowing anything to come in on my receive side. What a waste. I have a pair that is being used for transmit. I have a pair open that I could be used for receive of information from N2 to N1. I'm simply not using it. So full duplex was born, and it said, let's throw out that rule. Let's transmit and receive at the same time as long as there's no possibility, that's zero possibility of collisions. Now that was true on PCs that were connected back to back. But what can I do for my networked environments when I have more than two computers that need to share a common media? Now, up here, I had a common media, but it was a shared media, so I couldn't run full duplex. Then a switch came along, and it said simply this. I have a backplane that's known as a matrix. Within this matrix, I can create dedicated pipes. Instead of taking up the whole backplane, just dedicated from, let's say, N1 transmit pair to N2 receive pair. Now, I still have room within my matrix to have N4's transmit pair run to N1's receive pair. And I have two conversations happening simultaneously without the possibility of collision, as I said here. So let's see what that does to CSMA CD. This is our shared bus algorithm that we need for collisions. First of all, carrier sense. Do I need that in this media? Are there multiple computers that can access this at the same time? No, it's a single dedicated link. So I don't need carrier sense because there is no multiple access. And because of that, collisions are not a possibility. So I can turn this off. Anytime I'm running full duplex, CSMA CD is off. Another advantage to full duplex mode is that if I'm on a 10 meg network, I have a transmit capacity of 10 meg and a receive capacity at 10 meg simultaneously. Essentially, 20 meg of throughput on a 10 meg network. Now that you know the differences between half and full duplex, a general rule should be run half duplex when you have to and run full duplex anytime you can. In this nugget, we have defined a MAC address. We looked at MAC discovery via ARP. We outlined the CSMA CD process. We also discussed two duplex modes. I hope this has been informative for you, and I'd like to thank you for viewing.